Hello and good evening, everyone. My name is David Dimitri, and I am the Program Director at Headwater Science Institute. And I'm very excited to welcome you to night one of our student presentations for this year's summer research experience. Now, we've had over 20 students take part in our research program this summer, and over the next 3 nights, they're going to share all of their hard work with you. And you're also going to have the opportunity to meet their amazing mentors. So before we jump into our presentations for tonight, I just wanted to let everyone know that the presentations tonight are a great example of what other students can do as part of the upcoming fall research experience that we're going to be kicking off in September. So for family members, friends, and teachers watching out there who think this too could be a great experience for a student you know, or if you're a student interested in joining us for our next research experience, please be sure to check out all the details at our website, headwaterscienceinstitute.org, or at the link below. All right, so let's get into tonight's presentations. For those of you watching live on YouTube or Facebook Live, we encourage you to share any questions or comments you have for our researchers. And now I'm very excited to welcome our first mentor, Morgan. Hello, Morgan.
Hi. Sorry about the technical difficulties. Can you hear me?
I can hear you well. Yeah, thanks. So we're going to let Morgan go ahead and take it away to introduce our first researcher for tonight.
Perfect. Thanks, David. So my name's Morgan. I am a graduate student at the University of Nevada, Reno, where I work with wildlife diseases. And so today I am introducing my student, Aiden Peterson. He is a high schooler in Truckee and is also a competitive downhill skier. So he had the added challenge this summer of juggling not only this program, but also his training for skiing. He has been absolutely wonderful to work with this summer, coming to each meeting with really great ideas and questions, and just really excited to talk about his progress each week. So with that, Aiden, I think I'm gonna let you take it from here.
Awesome. Thank you, Morgan. Hi, everyone. My name is Aiden Peterson, and my project was tree decay inside of versus outside of ski resorts. First, I'll start off by talking about why I chose to study ski resorts. Ski resorts are large areas of land bought and dedicated to snow sports, but they often use toxic and harmful chemicals to keep conditions at a preferable point and equipment at peak condition. Ski wax is a special wax melted onto skis to help them glide across snow faster, but contains some of those toxic substances I mentioned before, known as per and polyfluoroalkyl substances, or PFASs. PFASs are some of the many chemicals in ski wax and can be found in high levels at ski resorts. These fluorinated substances have been found to be cancer-causing agents in humans, but I haven't come across any studies conducted to assess their effects on tree decay. Tree decay is the process by which trees are broken down, and it provides a source of food and shelter to many organisms at several different levels. I chose to research this area because if tree decay is being impacted, then it could disrupt food sources and shelters for animals, and with rising concerns over decreasing biodiversity, this experiment could tell us if this is also a concern for ski resort areas, and more specifically, those in Tahoe. For my experiment, I observed trees in areas likely to have low versus high levels of PFAS to see if natural tree decay was being impacted and how. My research question was, are Jeffrey pine trees located in ski resorts experiencing different rates of decay compared to those outside of ski resorts? My independent variable was location, so ski resorts versus non-ski resort areas, and my dependent variable was our measurement of decay, so this was number of dead branches, number of fungal bodies, and number of wounds weeping sap on our trees. My hypothesis was that Jeffrey pine trees living in ski resorts would see greater rates of decay compared to those outside of ski resorts. For my experiment, I visited 4 locations. 2 of them were in ski resorts and 2 of them were outside of ski resorts. In each of my locations, I measured 15 trees, and I measured the number of dead branches, number of fungal bodies, and number of wounds weeping sap. During observation, I eliminated bias by using transect lines to observe trees at random. However, some sources of error might include temperature and chemical changes between our locations. Here's a map of our locations. North Star and Squaw are our ski resort locations, marked in light green. And our non-ski resort locations are Donner Party Picnic Area and the Truckee River, which are marked in dark green. For my experiment, I tried to eliminate as many other variables as possible by measuring circumference, dBH, number of new and fallen trees, water and light availabilities, and I tried to keep the landscapes consistent too. I collected my data in the summer to ensure that all of the trees were totally available for observation and that nothing was concealed by any snow coverage. The only material you'll need for this project is a tape measure, and that's primarily for measuring circumference. Here are our results. I have 3 graphs, one for each measurement of decay, the first being the average number of dead branches in our different locations. The light green bars are our ski resorts, North Star and Squaw, and the dark green bars are our non-ski resort locations, Donner Party Picnic Area, and Truckee River. As you can see, our ski resort locations appear to have fewer number of dead branches on average than our non-ski resort locations, and when I ran a statistical ANOVA test to confirm this, I got a p-value of 0, which does indeed mean that we had statistically significant results. Here, in our second graph of average number of fungal bodies in different locations, we see the same trend where ski resorts see less decay than our non-ski resort areas. I ran another ANOVA test for this set of data and came back with another p-value of 0. For our final graph of average number of wound sweeping sap in different locations, we again see the same trend, and we got a p-value of 0 for this ANOVA test too. This means that all of our results were statistically significant. For our statistical analysis, like I've been talking about, I ran a series of ANOVA tests to determine if there was any difference in our data sets, and then I ran a series of t-tests to tell me where those differences were. As you can see in the table below, I have marked the p-values of our t-tests, and highlighted in green is our significant results when we compare to ski resorts to our non-ski resort areas. In figures 2, 3, and 4 of my results, which were my graphs, there was a significant difference between the measurement of decay in ski resorts versus non-ski resort areas. This tells us that ski resorts are seeing significantly lower levels of decay than in non-ski resort areas. I believe this is due to the hydrophobic properties of PFAS transferring onto tree surfaces in ski resorts and preventing excess water accumulation from high levels of snow in the winter. It's important to note that this change in decay between our locations could also be the result of a number of other factors that we didn't test for or observe in our experiment. Like I said earlier, I haven't found any recorded data of an experiment like this, so this was a large step towards understanding how ski resorts and the substances they use are impacting plants. Based on our knowledge of the slower rates of decay tree decay in ski resorts and the importance of tree decay, we can start to question if animals are being impacted too. So in the future, we can improve upon this experiment by testing for PFAS levels in observed sites, testing for other chemicals in our sites, and then testing in more locations and in greater sample sizes. We could also test in a lab to ensure that no other variables are impacting observation that we haven't thought of. We can also test new things like examining animal migration patterns and species changes in ski resorts over the past 100 years. The reason I say 100 years is because that's how long ski resorts have generally been around. And so if ski resorts were causing a change, that's when we would likely see it. Thank you everyone for watching. Here are my works cited pages, and I believe we have some time for questions too.
Okay, awesome. Thanks, Aiden. That was really, really well done. Yeah, so I think that Aiden would be happy to take a question or two if there are any, but I can start things off. So Aiden, you mentioned in your discussion that there are potentially some additional factors that you didn't necessarily measure in your experiment. Can you talk about some ideas that you have of what some of those might be?
Yeah, so there are several, but I'll just start with 2 so we save time for some other questions. But the first is snow level differences in our locations. So I don't know if many of you know this, but ski resorts make their own snow. They have machines, and when it's freezing, they shoot water out of those machines, and it freezes and turns to snow. So ski resorts will end up with a lot more snow than locations outside of ski resorts, and that could definitely impact tree decay. And another thing would be salt. So you might not know this either, but ski resorts often use salt and they pour that on the snow. And that, I'm not going to get into all the details, but that basically makes the snow harder, which is more preferable for a lot of people to ski on. And so that could definitely have an impact on tree decay as well.
Okay, awesome. Thanks. Let's see. Yeah, I'm not seeing any other questions pop up here. Cool.
Yeah, so if we don't have any other questions for Aiden for today's presentation, thanks so much, Aiden, for that excellent research project. And also thank you, Morgan, for your great mentoring with Aiden this summer. We appreciate it.
Cool. Thanks, David.
All right. So next, what we'll do is we'll go ahead and introduce our next mentor for the summer research experience. We have Michael out there. Hi, Michael. How are you?
Hi, I'm good. How are you?
You're doing very well. And Michael's going to go ahead and introduce our next researcher.
So my name is Michael. I am a graduate student at UNR. My interests include aquatic ecosystems and their responses to environmental stressors. And I would like to now introduce Richard Zhang, who is a high school student attending the Harker School. Richard will be presenting his topic on factors that influence chlorophyll and oxygen content in the San Francisco Bay.
Okay. Okay, thank you, Michael, for the introduction. So my name is Richard, and I will be presenting my research on the effects of various environmental factors on the algae and oxygen levels of San Francisco Bay. So let's get into the introduction. San Francisco Bay, or SFA, is the largest estuary on the US West Coast, and it has harboring high levels of biodiversity and providing recreational and economical livelihoods for the Bay Area's population of almost 8 million people. However, the Bay experiences intense algal blooms and a deterioration of water quality, and subspecies of algae can cause toxins, and intense blooms can lead to hypoxia as algae decompose. This has an environmental impact, an economic impact in terms of tourism, fishing, and other losses, but also an environmental justice aspect, as the homeless who depend on the waterways for food and live nearby are affected by the toxins. So there has been previous research done, and many studies also use the same data set that I did. First of all, Cloran et al. 2020 describes that the Bay has high nutrient levels in comparison to other estuaries and high potential for algae blooms, but the blooms are not recurring annually. Thompson et al. 2000 discusses other toxins such as polychlorinated biphenyls and mercury levels, and talks about sediment toxicity in the North and South Bay. Though that study was not directly related to the study of oxygen algae, contaminants might be inhibitors for algae, which were not in the dataset I used, but will be discussed in the discussion. So here are some definitions that I will refer to in this presentation. First of all, chlorophyll A is an indicator for algae, as algae photosynthesize with the pigment chlorophyll. SPM is suspended particulate matter, which essentially refers to particles floating in the water column. EC is extinction coefficient, which is a measure of photosynthetically active radiation, in essence, usable light that goes through each meter of water. And NO32 is nitrate and nitrite, two sources of inorganic nitrogen, which is a nutrient needed for algal growth. Diatoms are the major type of algae in the algal blooms in San Francisco Bay, and they use silica to form their shells, which affects one of my graphs later on. And finally, two numerical measurements that are that the level of chlorophyll A that suggests eutrophication is 20 micrograms per liter, and the level of oxygen that leads to hypoxia is 3 milligrams per liter. So my research question was, how do combinations of various factors manifest in the concentrations of algae and oxygen in San Francisco Bay? And I looked at the independent variables of chlorophyll A, suspended particulate matter, extinction coefficient, salinity, temperature, nitrate and nitrite, phosphate and silicate, and the dependent variables of chlorophyll A and oxygen. So my hypothesis was that if diatoms are marine and high temperature speeds up metabolism, algal growth would be correlated with high temperature, salinity, nutrients, and low SPM, since algae need light nutrients to grow. And since the decay of algal blooms leads to lower oxygen and warmer water holds less dissolved oxygen, high chlorophyll A and temperatures would lead to low oxygen levels. So I used the US Geological Survey's data from their SFA water monitoring project, looking at the years 2009 to 2019, but the data set did start collecting data in 1969. I used the 2019 data to run my regressions, but it was limited to only 20 different days of the year and only collected data from the stations on this map to the right, which are in the main channel of the bay. The data set had about 7,500 data points for salinity, chlorophyll A, temperature, and SPM, but only about 200 for nitrate, nitrite, phosphate, and silica. The programs I used were WaterPro, R, and RStudio. So this is my preliminary exploration. So I plotted averages and extrema by year, and the numbers did fluctuate year by year. However, the main takeaway is that hypoxia is not much of a concern in the main channel, while chlorophyll A is, as the oxygen level has not been measured to be hypoxic, but intense blooms do happen sometimes. So since extinction coefficient had around 200 terms, I wanted to see if that had a correlation with suspended particulate matter. And so since this is linear, I ended up using SPM for regression, since high SPM correlates with high extinction coefficient, which means low visibility. So the first regression that I made was of natural log of oxygen versus chlorophyll A and temperature. On the left side is a scatter plot of the raw data, and the coefficients of the regression are on the bottom. The last value right here is x1, x2, which is the two variables multiplied together, otherwise known as the interaction factor. The p-values are below 0.05, which means they are significant. And this regression predicts that oxygen is lowest at high chlorophyll and low temperature, while high temperature and high chlorophyll result in actually high oxygen, which surprised me. More on this in discussion. So here, the second regression was natural log chlorophyll A versus salinity and nitrate nitrite. This suggests that high nutrients and low salinity are more favorable. I was surprised to find that doing a regression of natural log chlorophyll A versus temperature and nitrate nitrite came out with insignificant high p-values, and those suggest that high temperature and nitrate nitrite will be favorable. There is a lot of variation in the data. Here are some other results. So LN chlorophyll A versus phosphate and nitrate is not significant in regard to phosphate, but is in regards to nitrate nitrite, suggesting nitrate nitrite is more limiting nutrient and should be more paid attention to, etc. I think I'm a little short on time, so I'm going to move on. So here's the discussion. Chlorophyll A and temperature are good indicators for oxygen, but chlorophyll A is harder to model with two factors. My model suggests that algae at a higher enough temperature generally makes enough oxygen to offset its use, and oxygen isn't much of a concern. And the average oxygen is around 8 milligrams per liter, which is healthy, and it does not drop below 3. In terms of error, there was less nutrient data, around 200 data points in comparison to 7,000, which leads to more variation and uncertainty. Moreover, only about 20 days were sampled, so algal bloom may have been missed in the time frame between measurements. Blooms also might be more common in smaller channels of the bay instead of the deeper main channel. Algae also have different ideal temperatures and salinities, so different types of algae in the bay might have affected this. Also, 2019 did not experience a large bloom. Like, its maximum chlorophyll A was 22.6 micrograms per liter. So maybe 2013, 2016, or 2018 would be better, as they had larger blooms with max chlorophyll A of over 80 micrograms per liter. In terms of my hypothesis, I was surprised that I was mostly wrong. So I hypothesized that diatoms would prefer higher ideal salinities, but the diatoms in the bay might be different species, so they are adapted for lower salinity. I also have hypothesis that low suspended particulates would be preferred, but instead higher SPM had correlations with high chlorophyll A. And this suggests that there are possible essential nutrients in SPM not accounted for, or maybe algae also count as SPM. Also, I hypothesized that high chlorophyll A and temperature would lead to lower oxygen, but the opposite is true, and at moderate levels of chlorophyll A, like the max in 2019 was 22.6 micrograms per liter, algae should produce more oxygen than the decay removes from the water. However, I'm not fully convinced that this is the case in general, and it might be a bell curve, and oxygen may be at much higher levels. So I'll quickly wrap this up with future research. So I'd like to redo these models with data for multiple years to include the high bloom data that my model lacks. I'd like to take data from outside the main channel of the bay to find other external, like from wastewater treatment plants, for example. I'd also like to analyze SPM in case there are inhibitors or something I haven't taken account of. Also, types of algae in different blooms, current, because this is in the main channel, and it might be more of a problem in smaller channels, and etc. Okay, here are my works cited, and are there any questions?
Thank you, Richard. So if anybody has any questions, please comment either on YouTube or Facebook. So the first question that we see here, were there any factors not included in the data set that you would have found useful?
Of course. I'd like to see different chemicals such as mercury or like biphenyls that are generally considered toxins to see if they have an effect on algae, and also current, because in terms of how like nutrients are moved around in the water.
And then another question is, would you expect to find the same or similar results if this analysis was done on smaller water bodies?
Yeah, of course, especially since the Bay experiences so much economic activity, like with all like the shipping. There's bound to be a lot more chemicals in the Bay than in like a smaller water body, so I expect different results.
Alrighty, thank you.
Thank you.
Yeah. All right, Richard, thank you so much for that great presentation. And thanks, Michael, for your mentoring with Richard this summer. Appreciate it. So next up, we are actually going to keep a theme going here a little bit with algal research. And I'm going to bring on our next mentor, Daniel Dudek, and he will introduce our next researcher.
All right. Hey there, everyone. My name is Daniel Dudek. I'm a recurring mentor at Headwater Science Institute, and I'm a PhD student at the University of Texas at Arlington. I mainly focus on sort of systematics, genetics, and ecology of amphibians and reptiles. But today, I'm excited to introduce you all to Ryan Bell. He's from Mill Valley, California, to talk about his work on cyanobacteria. All right, take it away.
All right. Hello. Oh yeah, I need to do screen share.
All right. All right, there we go, Ryan.
You guys see it? All right. So I'm doing what factors facilitate the growth of harmful algal blooms in Marin County lagoons. So my topic is there we go. My topic is what's causing toxin producing algal blooms to pollute Marin County's local waterways. So these are a significant threat because the production of harmful toxins harms organisms in the environment. They can suck up oxygen within large patches, creating dead zones that suffocate aquatic life, and they release harmful gases into the atmosphere. My research is on the presence of cyanobacteria and hepatotoxins, which are the most common toxins in freshwater blooms. And I am exploring water chemistry, meaning like different elements or compounds or whatever in water that might lead to the growth of HEBs, which are harmful algal blooms. There we go. So we're looking at factors that might aid their growth. From my background research, it seems that nutrients that come from runoff, sewage, and soil erosion may facilitate the presence of phosphorus, which is one of the minerals or nutrients that leads to algal growth. We believe higher water temperatures also help algae grow, and low turbidity. which means there's little movement in the water. It's still and unchanging, and sustained exposure to sunlight. The economic impacts posed include $82 million in losses to seafood restaurant and tourism industries, and a reduction in visits in terms of tourism, closure of beaches, decrease in catches for fishers, etc. Okay, so my research question is, as the title indicates, what factors facilitate the growth of harmful algal blooms in water bodies in Warren County? My independent variable was the location of study, because I had these 5 sites. My dependent variables were each of the attributes tested, which are pH, carbonate levels, chlorine levels, alkalinity, the presence of algal toxins, like just whether or not they're there, E. coli and coliform levels, temperature, and total dissolved solids. And my control for the experiment was Phoenix Lake, because it's a reservoir which local volunteers and water workers treat. So we believe that wouldn't have algae, and we were comparing that to the rest of the sites, which may have had algae. So my hypothesis is based on a null hypothesis. If you look it up, it's something that assumes that there is no variability with respect to the water quality metrics. The general definition of it is that it assumes no significant deviation in dependent variables. So I performed a few different tests to test different metrics. So I used a container of test strips, 10 per site. I used 10 total test kits to determine whether each site was positive or negative, 2 per site. I used I also tested bacterial presence, but that turned up to be statistically insignificant in my results, so I did not include that in my results section. And I also tested water temperature and mineral concentration and total dissolved solids. And this goes through my hypothesis. One assumes that there will be no variability. The other is the exact opposite, and it disproves the null hypothesis for each of the dependent variables, which assumes that there will be significant variability between each metric and each site. So I had a few different methods for collecting data. One of them was the test strips. It basically involved dipping them in water and comparing the resulting colors to these labels on the back, a total of 10 times per site. Part 2 was the presence of algae itself. The picture on the right shows a negative test where there's only one line on the right. And my third one used a meter that measured both temperature and total dissolved solids. This is a map of where I tested all of my locations. All right, so my results are shown in graphs. The following, a p-value up here of above 0.05 means they are not significant. This one was significant because this one's below 0.05. This one is extremely significant because it is amongst the lowest p-values I found. This one is also extremely significant. You had very low alkalinity at positive sites and very high at negative sites, for example. Chlorine is equally significant. Temperature, interestingly enough, turned out to not be significant between the sites. That is a very high p-value. And TDS was rather significant as well. Okay, so 2 sites, the Phoenix Lake, which was my control site, and the Tiburon site, tested negative. It was not expected that I'd have an additional site test negative, but this is what occurred in my experiment. 3 sites, Corte Madera, Strawberry, and Rodeo Beach, tested positive for the presence. So water temperature was a very poor indicator of whether or not algae would grow harmful algae would grow at the site. Chlorine, alkalinity, carbonate, TDS, and pH were all critical indicators. Water temperature, the water temperature corroborates the null hypothesis that there is no significant variation between the sites. All other metrics correlate the alternative hypothesis, which means that there is significant variation between each site. All right, and then Overall results indicate that high mineral presence, alkalinity, carbonate levels, chlorine levels, and lower pH, which are the most significant metrics in my experiment, might bring about or facilitate toxic algal blooms, and temperature was a very unreliable indicator. There were some shortcomings or errors, such as human errors in matching the test strip colors, because I had to visually look between the test strips, and I might have there might have been inaccuracies with that. There were the test strip colors only had a few specific values. So if you have pool test strips or whatever, they only have like a few numerical values, like 80, 120, 360. Some sites were very extreme, providing for exaggerated means. Like Tiburon had very, very high carbonate levels, like 360, which was the max on the test strips. And TDS readings were in the 4,000s in parts per million at Rodeo Lagoon, because we were right next to the ocean, which means it might be have high salinity or saltwater content. And we had some accidents early on involving the blue-green algae test, involving not tilting the tube properly during when placing it in the body of water or allowing water to leak out of it. Future research, we lacked equipment for measuring turbidity, which was one of the most important aspects of what might facilitate the growth of harmful algal blooms. And this has been covered in other experiments related to this field of study, but we did not cover that. We need further investigation of isolated inland waterways, because we tested some near the ocean and bay, which are easier to permeate with satellites that collect the data more easily. We need hands-on testing from volunteers to reach areas that these satellites cannot permeate, and further investigation on sunlight levels, because I did not measure sunlight exposure. And here's my works cited. All right.
All right. Thank you, Ryan, for the presentation. I will say we're going to be running a little late as of that point. But just real quick, tell us one of your favorite things, or one thing that you might want to improve on your experiment.
I think I need to measure more variables, because we were also measuring like the hardness of the water, which is related to TDS on the test strips. And we ended up having almost the hardness of every single site went completely off the scale on the test strip, because we were measuring waters with very high mineral content or salt content. And also I had some metrics that we didn't test enough, like we only did 2 phosphorus trials, so I didn't include it in my presentation.
Yeah, that definitely would have been great to see the results for that. But thank you again, Ryan. Good job. All right, so next, I had the opportunity to sort of mentor Claudia Fahn, who tackled this awesome project pertaining to wildfires in California. So a very, very hot topic, literally. So Claudia, take it away.
Okay. Hopefully you can see my screen. Great. Hi guys. So today I'm going to be talking about the correlations between precipitation and wildfires in California. And to give a little bit of overview and the reason why I chose to do this topic, California has been in a drought since like 2000, and the consequences of this kind of include rising temperatures and wildfires, and the results of this have been like detrimental. Just to give some statistics to back this up, in 2020, almost 4.3 million acres were burned by wildfires, over 10,000 structures were destroyed, and there were like 33 fatalities. So this is a really serious issue right now in California. So this really brought me to think of the question, does the lack of rain or precipitation levels impact the amount of wildfires? Because living in California, I have noticed that throughout the years that there's been less and less rain each year and more wildfires. And since there's an urgency of slowing global warming, climate change, wildfires once again been an issue. The reason why I wanted to, I guess, analyze the data from both variables is to create some sort of equation to predict the numbers of acres that will be burned given the precipitation levels for a given year. So I guess further action can be taken for prevention or whatnot. And also National Geographic has done lots of research that have linked wildfires to global warming too. So my research question was that, is there a significant relationship between precipitation and wildfires in California? My independent variable is precipitation levels in inches, which is basically the amount of rain. And the dependent variable is acres burned by wildfires. And my null hypothesis is that there's no significant relationship between the two. And my alternate is there is a significant relationship. And then my prediction is that I believe that higher precipitation levels will lead to fewer wildfires. So I mainly used data from government databases. For wildfires, I used CAL FIRE. This is what the data look like. I used data all the way back to 2013 to 2020. And how I collected my data was that, here's an example. This is a 2020 incidence. And I also separated all my data by counties. So for example, for Alameda County, you would add up the amount of acres burned and put that on an Excel sheet and do that for every single county. And then for precipitation, I use the NCDC, which is part of the NOAA, which is the National Oceanic and Atmospheric Administration. And you would basically plot in your points onto this graph, and then you would plot it into this data sheet. And for example, once again, for Alameda County, from January 2013 to December 2013, there were 5.08 inches of precipitation or rain. And I did that all the way up to 2022. And for my methods, I used Excel to perform linear regressions on all my data points. I also used it to graph a linear residual plot when I determined that the linear regression model was actually not the best fit for my data and the polynomial regression plot was, but I'll explain more of that in my analysis. And basically, once you plot all your data onto like a scatter plot, you can add a trend line, which determines the equation of the data. And there are different options here. And yeah. Also, you can find the R-squared valued, which explains the percentage of variation from the dependent variable to the independent variable. Basically, how much of the precipitation, how much of the acres burned is explained by precipitation. So I analyzed my results in 3 different ways. The first way is to take the average acres burned of all different counties in California for each year and plot it onto one plot. And I found that this gave me a really low R-squared value of about 1%. So that's when I decided to see if I could plot a residual plot to see if this is the best fit. So this is the residual plot. And in order to determine whether or not the linear model is the best fit, you have to see if the points on the plot are random. And here you can clearly see that there is this curve and that the data actually scopes out, so it's not random. So that's when I decided to use the polynomial regression. So this is the same data from the previous slide on a polynomial regression plot. And as you can see, the R-squared value doubled to about 2%, which is not great, but still. There's still a relationship between the two. The second way I analyzed my data was by year. So this is my data for of the year 2015 and the numbers of acre burned for each county. And this is the graph. So I got an R-squared value of about 10% for the year of 2015. Although you may notice that there are actually holes in my data, and this is because for some counties in 2015, there were no wildfires. Therefore, I could not plot it onto the plot because that would create holes in the graph too. And that wouldn't work for the model. So then finally, I decided to analyze the data by county. So this is an example of data of Amador County, which I plotted here. This produced this type of analyses produced the higher R-squared value for all my data, and it was more specific to each county. For example, here, Amador has an R-squared value of about 26%. So here is the data table of all the counties I was able to perform the same polynomial regression on as Amador. And I've highlighted ones that are pretty significant with an R-squared of about 40% or higher. And the one I bolded, which is Humboldt, has an R-squared value of about 71%, which is extremely high. I also calculated the mean and median to see whether the outliers would influence them, and they are relatively close. So, yeah. Moving on to the discussion. For the results of the total data, although the average data had about an R-squared value about 2%, which is relatively low, there still is a relationship between the two variables, although it may be insignificant. And the main explanation for this is that both variables, precipitation and wildfires, are independent variables and both natural phenomenon. So I'm not too surprised that they didn't influence each other as much as I thought it would. However, there's still correlation between the two variables in the different types of analyses, like per county. For example, in Humboldt, the R-squared value was 71%, which is extremely significant. And this means that about 71% of total acres burned per year in Humboldt can be explained by the precipitation. So if you were to calculate the numbers of acres burned in 2021, given the total amount of precipitation in Humboldt, the equation given from the polynomial regression would be pretty reliable. Since there was a non-significant relationship between precipitation and wildfires in the entirety of California, not just even though there was in some specific counties, there may be some other variables that could influence California wildfires, like temperature, air quality, wind, or even air pressure. So in the future, I could possibly look into these. Thank you for listening, and these are my works cited.
All right, great job, Claudia. Looks like we have some questions here. Does the CAL FIRE data include fires in national forests or just state forests?
I'm pretty sure all the data was just in California, and everything was separated by counties, so I'm not sure if like the forests were in each counties. So I hope that answers your question.
Yeah, I don't think when we were looking at the data, it sort of discriminated between national forests, but yeah. Okay, here's another one. So it would be interesting to see if there's data stored on the number of lightning strikes by region in California. Yeah. Yeah,
I agree.
So one question I have for you, specific to your results, why do you think, like, what are some factors do you think Humboldt County, did you do any sort of research about that specific county on why, there was such this really nice relationship?
I honestly did not do too much research on this county. However, I do know that in some counties, in certain years, there were like extreme outliers in the number of wildfires, like acres burned. Like one year in 2013, there could be about 100 acres burned, but then in 2016, it would be like 10,000 acres burned. So I think that would have influenced the R-squared value.
All right, Claudia. Well, thank you very much.
Thank you.
Yeah, thank you, Claudia, very much for that awesome research. And Dan, thank you so much for your mentoring with both Claudia and Ryan this summer. All right, we will next bring on our mentor, Beth Fitzpatrick, who is going to go ahead and introduce our next student researcher for the summer.
Hi, so yeah, my name is Beth Fitzpatrick, and just a little bit about myself. I am finishing up my dissertation in ecology at the University of Wyoming. And my research interests include understanding the effect of development on wildlife species distributions and their population dynamics. All right, so the exciting part is I get to introduce Caitlin Capitolo, who will be presenting her research, and she is going into the 10th grade at the Branson School. And she was really interested in this specific research project because, like the previous speaker, was really interested in the drought in California, particularly because it really affects her day-to-day life. So I'm going to let her take it away.
Good evening, everyone. So today I'm going to be talking to you about the 2010 to 2018 California drought through the lens of coho salmon migration. Sorry. So, as many of you know, California has faced drought troubles for a long time now, and California faced the longest duration of drought between December 27, 2011, and March 5th, 2019. This figure shows the severity of drought over time, and the darker the color, the more severe the drought was at that point. And on the x-axis, we have time, and on the y-axis, we have the percentage of land affected in California. Drought not only affects how long we can enjoy our nice, warm, and relaxing showers, but it also affects the living things around us. One species specifically that has been affected is coho salmon. Coho salmon typically migrate between mid-November and mid-January. Salmon need water to survive, and due to the long drought, their habitat has been tampered with, especially the discharge, which is the volumetric flow rate of water, and gauge height, or water levels. As of today, there are limited studies on the effects of drought on salmon migration because each watershed has to be looked at independently. However, it is a fact that climate change negatively impacts coho salmon. So, I have conducted a research project by diving into the question, how has the drought between 2010 and 2018 impacted the migration of coho salmon through Northern California? I hypothesized that the drought caused the amount of coho salmon that migrate through California to decrease. My independent variables were discharge and gauge height, and my dependent variable was salmon count. So, for my research project, I used pre-existing data sets from USGS and CNRA between 2010 and 2018, and Microsoft Excel for my data analysis. My data collection process and analysis was quite simple. I selected 3 locations in Northern California with coho salmon, which were Lagunitas Creek, the Eel River, and Redwood Creek. And then I chose the water flow and quality parameters on the USGS site, such as gauge height, discharge, and temperature. After that, I selected the time period between December 1st and 31st from 2010 to 2018. However, I did not include 2011 and 2017 due to time constraints. So once I collected the data from USGS and inserted it into Microsoft Excel, I calculated the averages for gauge height and discharge from each year. And I finally ran a linear regression using the average discharge and gauge height per year. And here are my results after running my linear regression for salmon count versus discharge. Each point displays the salmon count in accordance with the discharge levels. On my x-axis, I have discharge in cubic feet per second, and on my y-axis, I have the salmon count. The trend line shows us our linear regression R-squared value of 0.122 and a p-value of 0.13. As a result, since our p-value is greater than 0.05, there is an insignificant correlation between discharge and the number of salmon. So here are my results after running my linear regression for salmon count versus gauge height. Again, each point displays the salmon count in accordance with the gauge height, and the trend line shows us our linear regression R-squared value of 0.228 and a p-value of 0.033. On my x-axis, I have gauge height in feet, and on my y-axis, I have the salmon count. Subsequently, there is a positive and significant correlation between the gauge height and the number of salmon. So, based on the gauge height linear regression, there is a significant result, and drought impacts salmon migration. This makes sense because drought affects rainfall and snowmelt, and therefore water levels, which affect salmon habitats. Conversely, based on the discharge linear regression, there is an insignificant result, and drought does not impact salmon migration. However, given more time in terms of data collection, there is a potential for a significant relationship between discharge and salmon count. Additionally, the Eel River is a much larger water system than the Lagunitas Creek and Redwood Creek, so it caused some outliers in the data. It is also important to take away that droughts are affecting more than just the amount of water us humans can use. It's also affecting the living things around us, and coho salmon are just a small fraction of that number. So for future research regarding this topic, I think it would be beneficial to collect data from more years and different locations, test more parameters such as temperature, test how variations in the size of water systems affect the data, and or collect data about different types of salmon. And here's my work cited. Thank you everyone for listening.
Awesome job, Caitlin. So you have one question. Was the gauge height based on the peak height or the mean height?
I'm pretty sure it was based on the mean height between the time period that I put into USGS, and then and then I calculated the averages of those years and put it into my data.
Yeah, so that was a lot of data that you had to look at. How often were they actually recording that data? Do you remember?
I know the data collection stopped at 2018, but I'm not sure how long they were actually recording for.
Okay, cool.
Yeah.
All right, Caitlin. Well, thank you so much for an excellent presentation and really cool research. We really appreciate you taking the time to share a bit about coho and the drought out in California with us today. And Beth, thank you so much for your excellent mentoring this summer with Caitlin.
Thank you.
All right, we will next bring up our next mentor, and we'll add Keely to our stream. Hello, Keely. How are you out there today? Welcome.
I'm doing awesome, David. How are you?
I'm doing well. Thanks. Really enjoying all the presentations so far. And I know we're going to have another great one coming up next with your students. So I will let you take it away.
Awesome. Thank you. Well, hello and thank you. It's been wonderful working with Headwaters again. Like David said, my name is Keely Rodriguez, and I'm a doctoral research student in the Ecology, Evolution, and Conservation Biology Department at the University of Nevada, Reno. And my graduate research investigates the innate immune system, specifically of frogs, and how it responds to a deadly fungal pathogen known as chytrid fungus. And I'm so honored to introduce my student, Lauren Holm. She is a sophomore at Los Altos High School in Los Altos, California. And she joined Headwaters Science Institute after excelling in her biology honors course. And Lauren has been an organized and really hard worker through these last few weeks, and it's been my pleasure to work with her. Her talk will cover her meta-analysis of COVID-19 and wastewater and vaccination rates. So without further ado, I will turn it over to Lauren.
Hi, everyone. Thank you, Keely, for that introduction. So yeah, tonight I'm going to be talking about SARS-CoV-2 RNA, or viral COVID particles in wastewater, as well as vaccination rates. And I'm specifically going to be looking at data from Los Angeles County. So to begin, as we all know, the COVID-19 pandemic has impacted us all immensely over the past couple of years. The first case of COVID was discovered in late 2019 and is believed to have started in Wuhan, China. And in late 2020, the Pfizer and Moderna vaccine were approved for emergency authorization, and that is when California residents began receiving the vaccine. And then as for wastewater, wastewater can actually be tested for SARS-CoV-2 RNA through what's called a polymerase chain reaction, or PCR. And what's commonly used to test wastewater is called a reverse transcription PCR protocol. And to clarify a term I'm going to be using a lot, PCR units. It's basically a single region of RNA, and one genomic unit is equal to one viral particle. And as I said, we're going to be looking at data from LA County. So to begin, my research question was, how does the presence of SARS-CoV-2 RNA in wastewater fluctuate based on the rising COVID-19 vaccination rates in LA County, California? My independent variables were the vaccination rates. The dependent variable were the COVID PCR units in the water. And I hypothesized that the presence of the RNA in wastewater would decrease as vaccination rates increase, because the goal of the vaccine is to make people immune to the virus, and therefore slow the spread. And then as a result, there would hopefully be fewer viral particles present in the water. So for my methods and materials, the data that I used to analyze in this project was obtained from the Los Angeles County Sanitation Districts and California All, and all the data is available on their websites if you do a little bit of searching with it. And to analyze my data, I used a generalized linear regression in Excel. And another brief thing is PCR is used to quantify genomic units. And then on the side right here, we have a photo of just a brief visual of how sampling PCR works that I got from the CDC. So, after you get the sample of the water, it goes through sample concentration and then an RNA extraction, and then after that, you are going to actually measure your results, such as from human fecal matter and etc. So here are my main results. We have the percentage of the eligible population vaccinated on the x-axis, and then the PCR units in the water on the y-axis. We have my R-squared value was 0.2254, and an R-squared value is pretty much the measure of variation in the dependent variable explained by the independent variable. And I will then, over here, here is a little bit of a closer up graphs of just the PCR units in the water and then just the vaccination rates. So on the left, we have the wastewater, and then the dates are the same on both graphs. And then the right, we have the vaccination rate. So we can just look at that data individually. We can see that the PCR units, really increased in December and then drastically dropped and then consistently started to decrease and then eventually stayed at 0. And then we can also see that there's a pretty consistent increase in the vaccination rates. So the discussion, as I said, there was a huge spike in the PCR units that were present in the wastewater in December, which is interesting because that is when California residents began receiving the vaccine. However, that could be because due to travel, because a lot of people did travel during the holidays, so late November and December. And on the right, we can see a graph of how the COVID-19 cases changed around that time. And therefore, that is likely the reason why there were more particles in the water. And then the PCR slowly started to decrease and eventually stayed at 0, meaning that there were no viral COVID particles detected in the water. And then next we have, so the results of my research did support my hypothesis because my data suggested that as vaccination rates increased, the SARS-CoV-2 RNA in wastewater would decrease. However, some factors that may have not given me the most accurate results are that the people eligible to actually receive the vaccine changed. So for instance, I'm sure many people remember that when the vaccine first came out, it was first very limited to, just healthcare workers, but it was, for 18 and older. Then it became 16 and older, and then Pfizer got approved for 12 and over. So that definitely could have had an impact on the vaccination rates. And then the wastewater in LA County was only tested twice a month. So there could have been other trends missing that I could have analyzed as well. So future research, one thing that I think would be interesting is comparing this data to data from other cities in the US or even cities in other countries, or even contributing to the process of collecting and analyzing that data. I think would be a really cool thing to experience. And as well as understanding virus shedding, because it was actually recently discovered that RNA can be detected in wastewater prior to an outbreak because people are able to shed the virus before contracting symptoms, if any. So understanding virus shedding is something that I think would be very interesting. And here are my works cited. Thank you all so much for listening.
Awesome. Thank you so much, Lauren. That was a great presentation. I have some questions here. Do you think that you would see the same patterns that you saw with this research with LA County? Do you think you would see that in like a smaller town?
It depends on where. I would say that it depends on where that smaller town is, because not, for example, in California, people are very fortunate to have been able to get vaccinated fairly quickly. But I know that in other states, not very many, the vaccination rates are very, very different, but so are the COVID cases. So I would say it kind of depends, but otherwise, yes, because as I said, the vaccine should help the spread of the virus.
Awesome. And was this data easy to get for multiple cities, or was it widely available, do you think?
No, it definitely did take a lot of time and patience to get access to all that data and a lot of calculations, especially for the vaccination rates. But so it definitely would be a project to do it for other cities as well.
Awesome. Great job. Thank you, Lauren.
Yes, Lauren, thank you so much for sharing and for kind of enlightening us a little bit more about the current pandemic and what we're going through with vaccinations and how that is affecting the environment. So we really appreciate that awesome work. Thanks for sharing. And Keely, thank you so much for an excellent job of mentoring this summer. All right. So finally tonight, I am lucky not only as the program director at Headwaters, but as a mentor to introduce our final two presenters, Ashley Hung and Michelle Liu, who I'm going to add to our stream here. Hello. So Ashley is now starting 11th grade at Palo Alto High School, and Michelle will be starting her senior year at the Harper School this fall. And what I've really enjoyed about working with both Ashley and Michelle has been their strong interest in this research that they are going to present on basically since day one when we first met to talk about their research interests, and they've really stuck with this project throughout the entire summer. And they've really been committed to overcoming the different issues with accessing the available data that they've used for this project they're going to talk about today. So with that, I'll let Ashley and Michelle take it away.
Okay, great. I'll just go over our presentation real quick. Thank you, David, for the introduction.
Yeah, so today Michelle and I will be presenting our project about the impact of construction on PM 2.5 level in relation to housing unit income bracket.
Yeah, and so to start off our introduction, we initially became interested in this topic because we were really interested in the housing system that California currently has in place. And we found that there's actually a lot of consistent countywide regulation limits across different counties in California. And this is leading to restriction of construction and development of affordable housing units, since California is currently undergoing a gentrification crisis, and cities are becoming unlivable for residents due to lack of affordable places to live. So basically, the way that California's housing system currently works is all cities are required to go submit a housing element every single 5-year cycle. And these housing elements basically stipulate the regional housing needs allocation, which is shortened to the RHNA, which correlates with 4 income groups: very low, low, moderate, and above moderate. And the RHNA basically designates how many houses need to be built for each of these 4 income groups. And as I mentioned earlier, we were really interested in investigating this RHNA further because we noticed that California currently is not upholding the standards that it's setting for itself for housing. And on the right, we also have a map of the counties in the San Francisco Bay Area, which is what our research is focusing on.
Yeah, so as an introduction to the health aspect of our project, Fine particulate matter, or PM2.5, is an air pollutant composed of many different particles such as nitrogen dioxide and elemental carbon. High concentrations of PM2.5 are released at construction sites. And for example, one study actually found that during working periods at construction sites, PM2.5 levels are increased by around 11%, which is very significant. Inhaling high concentrations of PM2.5 is associated with high mortality rate from respiratory diseases, as well as overall death rates. And the bottom line and the importance of this is that PM2.5 harms human health, so it's necessary to take precautions in order to lower the amounts released into the air.
Okay, yeah. So we wanted to kind of combine the two aspects that we just introduced in our research question, which is how does the development of housing units in a city from 2009 to 2014, which was California's fifth housing element cycle, correlate with its different income levels to affect the PM2.5 levels of Santa Clara County, San Mateo County, and Alameda County. So for our research, the independent variable was the income level designated to a certain housing location, and then our dependent variable was the resulting PM2.5 level at that location. So we hypothesized that if a city builds housing units in accordance to income level brackets, then a larger concentration of PM2.5 will be present in the housing areas of the lower income brackets. And therefore, this would cause greater adverse effects to the housing inhabitants, which is what we were really interested in researching because we wanted to see what kind of inequalities are currently in the housing system of California.
Yeah, so for materials and methods, we first found our 3 counties that we were using. So again, the Alameda, Santa Clara, and San Mateo counties. And we randomly selected 12 sites where new housing construction took place from cities within each of these counties. And of these 12 sites per county, we found 3 sites that were allocated for each of the income brackets that Michelle explained earlier. And again, those are the very low, low, moderate, and above moderate income brackets. And in order to find this data, we obtained the 2007 to 2014 housing element update documents from 12 cities within each county. And we found the addresses of the new housing construction sites in the housing element update that correlated with the income bracket that we were looking for. And after finding the address of the housing site, we used purpleair.com's PM2.5 sensor data to locate a PM2.5 sensor nearest to that address. And we recorded that PM2.5 number. On the right, there's a screenshot of the website we used, purpleair.com. And you can see that there are a bunch of sensors available, and they just display the PM2.5 level at that location. And finally, to find the percentage of the 2007 to 2014 RHNA requirement that was fulfilled by each county in the Bay Area, we obtained data from the San Francisco Bay Area counties 2007 to 2014 Regional Housing Need Allocation Progress Update document.
Yeah, so for results, as Ashley explained, we investigated 12 sites in every single county. So these are the 2 graphs that we obtained for Santa Clara County, and these graphs are from 2 different days where we observed the PM2.5 levels. So the x-axis is the housing sites built by income brackets in certain Santa Clara County cities, and our y-axis is PM2.5 levels at the construction site. So as you can see, we kind of color-coded the income brackets. So the first 3 cities were very low sites, the second 3 are low, the next 3 are moderate, and then the final 3 are above moderate. And what we found is that there's actually a negative correlation between the amount of income level and the resulting PM2.5 levels at housing sites in Santa Clara County. And for the first graph, our linear regression R-squared value was 0.1447. And for our second graph, our linear regression R-squared value was 0.4335. So as Ashley mentioned earlier, this negative correlation reveals that on average, lower income housing sites have higher PM2.5 levels, which is more harmful to human health for the inhabitants who live in those sites. 1 second.
Yeah, and we can see the same pattern in the Alameda County. So there's a negative correlation between the income bracket and the PM2.5 levels released at construction sites. And so on the left, on July 29th, the linear regression R squared is 0.0807, and on the right, the linear regression R squared is 0.0411.
And for some of the data county, we also found the same measure of correlation. So our graph on the left has an R squared value of 0.057, and our graph on the right has an R squared value of 0.109.
And this is the percentage of 2007 to 2014 RHNA met within the Bay Area counties. On the left, we have this in the form of a table. So we can see that Bay Area counties on average only met about 20 to 30% of their RHNA requirements for very low, low, and moderate income brackets. And on the other hand, they met about 99% of their above moderate RHNA requirements. And on the right, this is in the form of a graph. So we can see that there's a positive correlation between the income bracket and the resulting percentage of RHNA fulfilled. And from this graph, the p-value is less than 0.001, which is very significant.
Yeah, so basically what we found in our results was, and the first part was that lower income housing locations on average have higher PM2.5 levels than their high income counterparts. And as Ashley just explained in the previous slide, cities are failing to meet their RHNA for all income brackets except for above moderate. So this kind of proves our hypothesis because it shows how unenforced California's housing system has been, because there's no regulation put in place that requires cities to actually meet the RHNA for affordable housing units, while instead cities are building more unaffordable housing units for richer income inhabitants. Yeah, and some of the factors that could have influenced our results are PM2.5 levels from other construction sites that affected the levels at the housing site nearby, or other air pollution such as the wildfires. And on the right, we have a picture of the smoke in San Jose, California, which is one of the cities that we studied last year on Wednesday, August 19th. So some of that residue smoke might have influenced our PM2.5 data. But overall, our main conclusion is that California's current housing element system is failing to provide adequate affordable housing due to the lack of consistency and regulation, and is also harming citizens of lower income brackets and exacerbating gentrification. Sorry again.
Yeah, as some future research, these are some of our questions. So the first one is, what specific factors are leading to higher PM2.5 levels at lower income housing locations? For example, higher density population, proximity to roads, highways, all of these factors. How can efficient regulations be enacted in California to ensure that citizens living in lower income brackets receive fair housing? And in addition to this, what can be done to require that all cities fully meet their designated housing allocations for each income bracket? And lastly, are there any other explicit health effects caused by higher PM2.5 levels at lower income housing locations, other than, of course, our prior knowledge that PM2.5 causes adverse health effects? And yeah.
And then here's our slide for excited.
Yeah. And then we're excited for our images.
Thank you all for listening to our presentation.
All right. Thank you very much, Michelle and Ashley, for presenting on that. Awesome to see it all come together finally here on presentation night. We have some time for a question or two for Michelle and Ashley. So if anybody has one out there, I guess I'll start us off. This was a really interesting project in terms of what you had to do to get the data. What was the hardest part, do you think, of your data collection specifically as you were working with pre-existing remote data that you had to collect yourself?
I think the hardest part was definitely actually consolidating all the information from the different housing elements. And what we mentioned earlier was that there's a lack of consistency within like different cities or even different counties in California. So different cities would have their housing elements available on different websites, but there wasn't a consistent way that you could just access all the housing elements. And some cities didn't even submit, like for instance, annual progress reports, which they were supposed to be submitting every single year. Yeah, so definitely there's a lot of future research that could be done on this topic.
And similarly, at the beginning, we were focusing a lot more on the health aspect as well, but we found that it was difficult to obtain data relating to like mortality rates, especially due to something so specific like respiratory diseases. And there are so many other factors to that as well.
Excellent, great. Well, thanks for sharing a little insight into what it's like to be behind the scenes, so to speak, doing some of the research and collecting the data. All right, well, with that, we're going to go ahead and thank Ashley and Michelle for a great presentation. So thanks to you both. And what we're going to do is we're going to go ahead and wrap up night one of our student presentation. So I just wanted to thank all of our student researchers tonight for their hard work throughout this entire summer. We're very proud of each of you. I think everybody watching agrees. You have all done an excellent amount of work and just a great job putting together these fantastic projects this summer. For those of you that are watching that still have a question or a comment for any of our researchers, you can always please just drop those on YouTube or Facebook, and we'll make sure that our students see those and they can answer those at a later date. And again, if you're interested as a student, or if you know of a student who may be interested in joining us this September for our fall research experience, please be sure to head over to headwaterscienceinstitute.org to find out more details. And then I also wanted to thank, obviously, each of our mentors that you met tonight for their continued guidance for our students all summer long. And finally, thanks to all of you for watching. Just a reminder, tomorrow we will return again at 5:30 p.m. for night 2 of our presentations, so please be sure to join us then. Have a great night.